So in this and the next lecture, we'll look at some circuit theorems that allow us to simplify circuits or that enable easier solving of circuits. Let us begin by looking at this very simple circuit. It has a 20-volt voltage source connected in series with a 2-ohm resistor, and I've called the voltage source VA and the resistor RA. And currently in this circuit, the terminals A, B are shorted together. The same circuit is here with the terminals A and B open circuited. Here is another circuit where there is a current source Ix in parallel with a resistor Rx connected across terminals A, B, and here the terminals A, B are short circuited. Here they are open circuited. Now let's look at all these four circuits one by one. So in this circuit, the current I1 is of course VA by RA. In this circuit, the current I2 is Ix because no current will flow through Rx because Rx is shorted to itself. So the entire current Ix flows through the short circuit, and so I2 is Ix. In this circuit, this is an open circuit, so the voltage V1 is VA because no voltage falls across RA, so we get V1 equal to VA. Here we open circuit at AB, and the voltage V2 is Ix times Rx, right? So we get V2 equal to Rx times Ix. Okay, now let us compare this circuit with this circuit and say that suppose I want this I1 to be equal to this I2 and I want this V1 to be equal to this V2. Alright, so we say we want I1 equal to I2, and so we'll get Ix equal to VA by RA, which I have written here. And in this circuit, we want V1 equal to V2. V2 is Rx Ix. So Rx Ix. Ix is VA by RA. So Rx into VA by RA, and we want this to be equal to V1, which is VA. So VA cancels. And so we get Rx equal to RA. So we say if Ix in this circuit is equal to VA by RA, and if Rx is equal to RA, then this current and this current are equal, and this voltage and this voltage are equal. Alright, now let us take both these same networks and connect an 8 ohm resistor across them. So we have 20 volts 2 ohms. We just found out this is, okay, I'm sorry, we didn't put numbers. So, okay, so if VA is 20 volts and RA is 2 ohms, then Ix is VA by RA is 10 amperes and Rx is the same as RA, so it is 2 ohms. So we have 20 volts 2 ohms and 10 amps 2 ohms. So the 20 volts 2 ohms and 10 amps 2 ohms. Now we connect an 8 ohm across both these networks and find the current I. So the current I in this circuit is of course 20 volts by 10 ohms. So that is 2 amperes. And in this circuit, if we find the current by current division, so this current I will be 2 ohms divided by 2 plus 8 into 10, which is 2 amperes. This is 2 amperes. This is also 2 amperes. So what we find is that whenever we connect anything here, the current flowing in these two networks is the same if we had made this equal to VA by RA and this equal to RA. Alright, so now with this example, we state a theorem, and this theorem is called the source transformation theorem. So the theorem states that if there is a voltage source VA connected in series with a resistance RA across any network at terminals A and B, then this VA and RA can be replaced by a current source in parallel with a resistance across that same network, and if this current source value is VA by RA and this resistance is RA, then all the voltages and currents in this network in these two will remain the same. So if we replace VA and RA with IA and RA, then nothing changes in these two networks. This is the source transformation theorem. We have not proved this, we have demonstrated it. We are not going to prove theorems in this course, we are just going to assume that they are valid. If you are interested in learning how to prove, you have to do kind of detailed, go into detail into a field called network theory, which usually follows a course on circuit theory, which is what we are doing. We will not be doing network theory at in your IM Tech curriculum. But if you are interested, you can look it up on your own and ask me, I'll give you some references. All right. So this is source transformation. Let's look at some examples of source transformation. So let us say we have a 10 volt source in series with a 5 ohm resistor connected across this network, 8 ohm, 10 ohm, 20 volts. And if we replace this 10 volts and 5 ohms by a current source, 10 by 5 is 2 in parallel with 5, then this everything in this circuit should remain the same. So I have specifically put VA and I. So both these networks, VA and I, will remain the same. All right. Now I would like you to solve these two circuits. Pause this video, solve these two circuits and find VA and I. All right. Please pause, solve and then continue. I am going to continue, giving you a chance to pause. Okay. The answer is VA is equal to 160 by 17. The current I is equal to 18 by 17 in both the networks. So you check whether you've got these answers or not. Okay, here is a question. So we said a voltage source in series with a resistance can be transformed into a current source in parallel with the same resistance. How about transforming an ideal voltage source? What do you think? How will you transform an ideal voltage source to a current source? Think about this. You again pause the video again and think about how will you convert an ideal voltage source to a current source in parallel with a resistor. The answer is that an ideal voltage source cannot be transformed to an equivalent current source, and vice versa. An ideal current source cannot be transformed to a voltage source in series with a resistor. Okay. Let us look at another example. So here you have, so let's just look at this. So here you have 20 volt in series with 4 ohms and there is 2 amps in parallel with 5 ohms. So from here to here I am transforming this 20 volt and 4 ohm into a current source and resistance, same resistance, current is 20 by 4, 5. By the way, one has to be careful of the direction and polarity. Okay, I didn't mention this earlier. So if this is plus minus like this, then this current source, the direction of the current source must be such that the voltage across these two nodes due to this current source and this resistance will be the same as the voltage polarity across these two terminals. Alright, so one has to be careful. You put the wrong polarity, you will get all incorrect answers. Okay, so we have 20 volt 4 ohm replaced by 5 amps and 4 ohms. Now let's say our goal was to find this current I. So if we have this circuit, now we see that 5 amp and 2 amp are in parallel. So we can combine these two. So we get 7 amperes. And then we have a 4 ohm and a 5 ohm and we can apply voltage division. So we can say this current is equal to 4 divided by 9 times 7. So to find the current I in this circuit, of course we can do nodal analysis also, but here is a demonstration of using source transformation to find the current I. It is just another method that allows us to find the current I. Okay, let's look at one more example. So let's say we have 40 volts, 8 ohms, and then 4 ohms, 2 amperes. And we want to find the current. What do we want to find? The current I and the current I2. Alright, the goal is to find the current I and the current I2. That is a question. And we want to use source transformation. So, suppose we want to find the current I, and if we replace this 40 volt and 8 ohm by a current source in parallel with an 8 ohm, we would have lost information of this current I. This current I will not exist in the circuit where this voltage source and the 8 ohm are replaced by a current source in parallel with a resistance. Alright, so that's a property of source transformation, that when you source transform, the current in the original source is lost. Information of that current is lost. Alright, so in this circuit, if we want to apply source transformation, we'll transform this, the resistor in parallel with the current source, into a resistor in series with a voltage source. So same resistance, the voltage will be 4 times 2, 8 volts. And now we have a single loop and we can easily solve. So the voltage is 40 minus 8, 32 divided by 12. So we'll get 8 by 3 amperes. So we get the current I by transforming this. Similarly, if you want to find I2, so the current I2 does not exist in this circuit. I2 is lost because we transformed 2 amps and 4 ohms to a voltage source in series with the resistance. So if you want to find I2, we could have transformed 40 volts and 8 ohms to a current source in parallel with a resistor. Or of course there are other methods. Once we found I, see we found I here. So we know that this I is this I. So we know that this I is 8 by 3. We know this is 2. So we can do KCL at this node and find I2. Alright, so remember this, the property of source transformation, that the current and voltage in the original circuit that was transformed are lost when transformation is done. Alright, the next theorem we'll look at is superposition theorem. Perhaps you have seen this before. I don't know, some of you may have seen this in the 12th standard. Anyway, here is a circuit we looked at in lecture 5, slide 10, if you want to go back and look. And we had solved this circuit using, I think we had used nodal analysis to solve this circuit, and this was the answer. So we had found the voltage VB, and we had found VB to be this expression, which can be written as some constant A1 times Vs plus some resistance, equivalent resistance R1 times I0. Okay, so with this kind of simple circuit here to look at, we state superposition theorem. Superposition theorem states that given a linear network with n independent sources, so these sources can be current sources or voltage sources, a voltage VA at any node A in the circuit can be written as a sum of n terms. So n, if there are n independent sources, the voltage anywhere in the circuit can be written as a sum of n terms. Let us say VA1, VA2, VA3 up to VAN, where each of these terms is the voltage at that same node A due to independent source 1, with all the other sources made 0. Alright, so if we say VA is this, then we say VA1 is the voltage at node A due to the independent source 1, with all the other sources made 0. VA2 is the voltage at node A due to independent source 2 with all the other independent sources made 0, and so on. And similarly, any current in any branch in the circuit can be written like this. So this is a simple demonstration of that theorem. So the voltage VB in this circuit can be written as a sum of two terms, because there are two independent sources in this circuit. And if we find the voltage VB due to Vs by making I0 equal to 0, then we'll get this term. And if we find the voltage due to I0 by making Vs 0, then we'll get this term. And then we add these two, and then we get the total voltage. So this is superposition theorem. Superposition is actually very useful often while solving small circuits. So all these theorems are actually useful while solving small circuits. Okay, so let's look at an example. Okay, now before looking at an example, let's define a few terms. What is a linear network? Here it says this is valid for a linear network. What is a linear network? A linear network consists of linear circuit elements, which we have defined in our lecture 2, plus independent voltage and current sources. Alright, a linear network can consist of linear circuit elements plus independent voltage and current sources. So why do we say this? This is related to this question. Are independent voltage and current sources linear circuit elements? You think about this. Are they linear or not? You go back to your lecture 2 and see the definition of a linear circuit element and check if an independent voltage source is a linear element or not. Alright? You get the answer. You should get the answer very quickly, but you should check. Okay. The other thing we said is that while finding the voltage VA1 due to a source 1, we will make all other sources 0. So we must understand what making a source 0 means. So a 0 valued voltage source is a short circuit. So when I want to make a voltage source 0, I'll short circuit the two terminals across which it is connected. If I want to make a current source 0, I'll open circuit it. Alright, I think you know this already. Okay, remember, very important to remember, superposition cannot be applied to dependent sources. By that I mean, when we say that we have a network with n sources and we apply superposition, these are n independent sources. If there are dependent sources, they'll stay as they are. They'll not be counted as in the number of sources. Alright, we'll look at a couple of examples of this. So here is a very simple circuit, in fact the same circuit, and we know that the answer is this. VB is A1 Vs plus R1 I0. So let us apply superposition to find the voltage VB. So we say, well, I'll find VB due only to Vs first. So that is the circuit here. So we'll make I0 an open circuit. When we make I0 an open circuit, we get this circuit. And then the voltage VB can be found. So we call that voltage VB1 by voltage division, because this voltage is Vs. This voltage is Vs, and Vs divides between R2 and R3, and VB is the voltage across R3. So VB1 is R3 by R2 plus R3 into Vs. Then we find VB, we call VB2 only due to I0, and for that we short circuit Vs. So we short circuit Vs. So R1 goes away, it is short circuited, and so we get R2 in parallel with R3 across I0. So VB is I0 into the equivalent resistance of R2 parallel R3. So VB2 is R2 R3 by R2 plus R3 into I0. And the total VB then is this plus this, which is of course the same as this, thus demonstrating superposition theorem. Okay. As an aside, not related to superposition, note that VB the expressions for VB does not have R1 in it. There is an R1 in the circuit, and usually one would expect that in a circuit like this, any voltage would depend on all the resistances. But there is no R1 in this expression. This is interesting, but actually when one thinks about it, it is not surprising. And here is the reason it is not surprising. The reason this happens, and the case where it happens, is when a resistor is connected directly across a voltage source. A resistor connected directly across a voltage source does not affect the rest of the circuit. Whether this resistance is there or not, the rest of the circuit, all the voltages and currents are unaffected. Why is that? Because this R1, this voltage here at this node is Vs, because we have connected a voltage source across at that node Vs. So whether R1 is there or not, this voltage is always Vs, independent of R1. So R1 has no effect on the rest of the circuit because this voltage is forced to be Vs. All that R1 does is it carries a current itself, and it changes the current supplied by Vs. But the rest of the circuit is unaffected by the absence or presence of R1. Similarly, the same thing happens if you have a resistance in series with a current source. A resistance in a series with a current source has no effect on the rest of the circuit. Okay. Let us look at another example with a dependent source. So this has one independent source and one dependent source. And here, okay, so the first thing I have done is I have solved this circuit and written the answers here. You can solve it yourself. It's a very simple circuit. So you solve this and find Vx and find I. Alright, so okay. So now let us see if we can apply superposition to a dependent source and see what happens. So we try and see what happens. So you say, okay, I'm going to treat this also as a source to which I can apply superposition. So I'll say first I'll find the current I due to only the 10 volts, and I'll short circuit this voltage source. So we short circuit this voltage source and find the current I, and we call it I1. Now this is short circuited, this 4 ohm has short circuited to itself, there is no voltage across the 4 ohm, and so there is no current in the 4 ohm, so I1 is 0. Then we say, okay, what is the current I due to this dependent source while removing this voltage source? We short circuit this and we have this circuit. What is the current in this circuit? Okay, you check this. I'm going to come back to this circuit later, so I'm not discussing it. But you check this circuit. The answer is that I2 is 0. Alright, so I1 plus I2 is 0 if we apply superposition to a dependent source. But the actual current is 5/3 ampere. So this is a demonstration that superposition cannot be applied to dependent sources. It can be applied only to independent sources. Alright. Okay, so this is the end of this lecture. We'll continue next time.